Chapter 7, Part 3. In this lecture, we'll be talking about nuclear weapons, the term half-life as it relates to nuclear isotopes. We'll talk a little bit about nuclear waste, here today, here tomorrow, risks and benefits of nuclear power, and the potential future for nuclear power. There are two types of nuclear weapons, one that use only fission, and those that use actually both fission and fusion, with the majority of the explosion in fusion weapons coming from the fusion reactions, but they must be initiated by a fission reaction. It's almost impossible to create fusion reactions on Earth. They need very, very high temperatures in order to take place. Here, in this picture, to the upper right, there is shown a particle of deuterium, hydrogen with a neutron, and tritium, hydrogen with two neutrons. When those particles are combined or fused, they can form a helium nucleus and an extra neutron. When that occurs, the products are slightly lower in mass than the reactants, so that mass that was quote-unquote lost was in fact converted to energy. In order to start a fission reaction, in order to start a fusion reaction, we need a fission reaction because that fusion requires so much energy. This picture in the lower right is of a star, possibly representing our sun, where the temperatures are high enough for fusion reactions to take place. Please take a look at a video on uranium enrichment. So, uranium enrichment involves taking natural uranium, which is mostly uranium-238, and essentially trying to extract or enrich as much uranium-235 as possible. Most uranium used for fuel rods is only most uranium used for fuel rods is only 3 to 4% uranium-235 and cannot be used for weapons. But if we were to go on and enrich that further and further, then we would get what is called weapons-grade uranium that can be used for nuclear weapons. And as I mentioned at the beginning of the Chapter 7 lectures, it's this reason we chose uranium to run our nuclear power facilities, because it would have a dual purpose. One, it could be used in controlled nuclear reactions to generate electricity, and second, we could further enrich that uranium that we already have mined for our nuclear power plants to produce weapons-grade uranium. Now, as you'll see by the end of the lecture, there are other options besides uranium that may be much, much safer. We talked about chain reactions or controlled chain reactions in nuclear power plants. Basically bringing together enough uranium to initiate a chain reaction and then pulling apart the uranium, or separating the uranium so we slow or stop that chain reaction. What happens in a nuclear weapon is we essentially create an uncontrolled chain reaction. We have a critical mass of uranium in order for that to occur. What that means is you need a certain quantity of uranium density, essentially, in order for that reaction to be self-sustaining. More and more uranium nuclei split, creating more and more neutrons. And if those uranium atoms are close enough together, those neutrons will each hit another uranium atom, producing more neutrons and splitting more uranium atoms, and so on and so forth. One way this can be done in a nuclear weapon is to essentially fire two pieces of uranium at each other using a conventional explosive. So the conventional explosive launches one piece of uranium to another. Those pieces of uranium, when fused, have a critical mass, and then an uncontrolled chain reaction can occur, releasing an incredible amount of energy. Thinker buddy, what is meant by the term critical mass? A. Excess neutrons are produced and the result is likely to be a nuclear explosion. B. There's an immediate need to add more nuclear fuel to sustain the fission reaction. C. Water must be added to the reactor core to prevent potential meltdown. D. Enough radioactive material is present so a chain reaction can be sustained. D is correct. When we talk about critical mass, you have enough radioactive material so a chain reaction can be sustained. A is not entirely correct because in the fission of a uranium nuclei, for example, you will produce neutrons upon the nuclear reaction. But just the fact that there are neutrons produced doesn't always mean that you're going to have a nuclear explosion. An example would be the use of fuel rods in a nuclear power plant. Please watch the following videos on half-lives. So half-life is the time required for the level of radioactivity to fall to 1/2 of its value. In this example, we have on the left y-axis the intensity of radiation, and then on the x-axis we have years from 0 to about 100,000 years. And you can see it starts at 100%, time equals 0, 100% intensity, and then after about 24,000 years we have half of the original intensity of that radiation. This happens to be the half-life for Plutonium-239. Here are some half-lives for a number of radioisotopes or radioactive isotopes. And you can see they vary from millions of years, some of which are present in the fuel pellets used for nuclear reactors, and then to a number of days or even seconds. Some of these are produced during fission and need to be disposed of as nuclear waste. Thinker buddy, what is the half-life of the radioisotope X shown in this graph? The graph has on the y-axis percent radiation intensity starting at 100%, going down to 0, and on the x-axis 0 to 5 seconds. The curve slopes downwards somewhat exponentially and ends at 5 seconds. Is it A, 4 seconds, B, 3 seconds, C, 2 seconds, or D, 1 second? The correct answer is about 2 seconds. What we want to do is go from the 50% mark, draw a line over to our curve, and then draw a line down, and that will tell us what time it takes for 50% of the radiation to disappear. Please watch the following video on nuclear waste. So, some means of disposal of nuclear waste, particularly once the fuel rods lose their effectiveness as controllable chain reactions in the nuclear power plant, they are initially transferred to a water storage tank that also has boric acid in it to help contain any further radioactive or radiation release. They're meant to be in those water containment units until they cool, which should be only a few months, but often if there's no available room on site for storage, they can stay there for years. After a few months, when they should be taken out of the cooling ponds, then they're often stored on site. The picture in the upper right has those cylindrical towers. That's known as a dry cask storage system. And you can see people monitoring the safety and radiation release of those storage systems. The lower right-hand picture was an attempt at very long-term underground storage. The facility at Yucca Mountain was built, but then due to lobbying and other concerns regarding the long-term storage and groundwater contamination, unfortunately, after billions of dollars were spent on the facility, that plan was scrapped. So we still really don't have a very long-term storage of nuclear waste in the United States. Please watch the following videos on the risks of nuclear energy and the future of nuclear energy. You may be asked to discuss the debate on nuclear energy in a discussion post. This ends Chapter 7, Part 3, the last and final part of Chapter 7.